In this video, I want to talk about the intermolecular forces. Intermolecular forces are the forces which are available between the molecules, and these are weak forces compared to the forces which are available in the metals and in the ionic compounds. It says the forces of attraction between the different molecules of a substance are known as intermolecular forces. So these forces are available between the molecule, and we are talking about the attraction forces, the forces which keeps the molecule close to each other. If you look at the title, you know that the forces which keeps the molecule close together are the weak. So that's why the molecular compounds relative to the other type of the material, they have low melting point and boiling point, because the melting point and boiling point depends on the attraction between the base units. Because the attraction between the molecules is weak, it's very easy to separate them from each other. So at low temperature we have enough energy to overcome the attraction between the molecules. So it's very easy, we can melt them and we can evaporate them. But for the ionic compounds and metallic compounds, the attraction between the base unit of them are strong. So that's why if you want to separate the cation and anion in the ionic compounds, and you want to separate the atoms in the metallic structure, you need a lot of energy. So you need very high temperature uh, to overcome this attraction between them. So that's why the ionic compound and metallic compound, they have very high melting point. But in the molecular compounds which have weak attraction between their molecules, the melting point and the boiling points are small relative to what you have in ionic compound and metallic compounds. So I want to talk a little bit about the attraction between the base unit for different compounds. Let's talk about the ionic compounds first. So you know that the ionic compounds are composed of the cation and anion, and they have crystalline structure. So the cation and anion are connected to each other by electrostatic attraction, which are available between the oppositely charged particles. So the cation and anion are held together by these type of electrostatic attraction. This type of the attraction in the current compounds are called ionic bonds. So we have ionic bond here, and the ionic bond, which is attraction between the cation and anion, is strong. Okay, so if you want to melt the ionic compound, and or if you want to vaporize that, you have to overcome these attractions which are available between the ions to be able to separate them from each other and convert them to the liquid or gas. And it's not easy to overcome that one, so you need high temperature. Same thing you have in the metals, the metallic compound. In the metallic compound, you have the metal atoms in the delocalized electron or sea of electrons. So as we said earlier, the metals have low ionization energy, so at room temperature they easily lose their valence electron, and the valence electron are moving between the atoms, so they don't belong to any of these atoms. So you have the methyl cation here, and you have the sea of electrons here around them, which is resulted from the delocalized electron, and this sea of electrons are negative. So positive ions are kept in the negative sea of electrons, and again the attractions which are available between these negative area and these positive metal ions are very strong, so it's not easy to break them and to separate the atom. If you want to, for example, melt the metal, you have to overcome these attractions which is available between the cation and sea of electron to be able to separate them from the other atom. And here you have metallic bond, and the metallic bond is strong, so it's not easy to separate and melt them. So that's why ionic compound and metallic compound, as you can see here in this table, they have high boiling point as it's shown here. But what about the molecular compounds? Let's talk about the molecular compounds. First thing that we can note is that the molecular compounds, they have low boiling point. So this shows that the attraction between the molecules are not strong. The attraction is weak. So we can easily overcome those attractions. Now we want to talk about the attractions which are available between the molecules. We have two types of the molecules based on their polarity. Some of the molecules are polar and some of them are non-polar. You know that the polar molecule, I can show it by this one, they have a positive area and negative area in the molecule. So they have positive and negative area in the molecule. But the non-polar molecules, they don't have positive and negative area, and the electrons are evenly distributed between them. So the polar molecules, they have dipole. It means one side of the molecule, for example, for the water, this side is partially negative, other side of the molecule is partially positive. The definition of the dipole here is given in your textbook. It says a dipole is created by equal but opposite charges that are separated by a short distance. This happens when the two atoms which are bonded to each other has they have different electronegativities. For example, for the HCl molecule, you have only one bond. Chlorine is more electronegative, so it pulls the electron toward itself. It becomes partially negative, and hydrogen becomes partially positive. So if you look at the HCl molecule, the area around the chlorine is partially negative and around the hydrogen is partially positive. And in the previous videos, we determined which one of the atoms, or how we can determine if the molecule is polar or non-polar. So that concept is very important here. Let's talk about the attractions which are available between the polar molecules. Let's go back here. An example of polar molecule is ICl. Chlorine is more electronegative than iodine, so these electrons are pulled toward the chlorine. This area of the molecule becomes partially negative, the other area of the molecule becomes partially positive. So you can see a chlorine molecule here. This one is a chlorine molecule, or ICl molecule. Here is the I, this one is Cl, and it's polar. So when you have polar molecules, the molecules come close to each other in a way that negative area of the one molecule is attracted to the positive area of the adjacent molecule. Okay, this happens for all of the molecules. Look for this molecule, the positive area of the molecule is adjacent to the negative area of the other molecule. So they are oppositely charged, so they have some attraction between them. This type of the attraction is called dipole-dipole forces. So for the polar molecule, we have dipole-dipole attraction between them. But what about the non-polar molecules like CCl4 and CO2? Later on, we will talk what is the force of attraction which is available between the non-polar molecules. Non-polar molecules, they don't have positive and negative areas. So how they are attracted to each other? Later on, we talk about that one. But before talking about the non-polar molecules, let's say what happens if you mix a polar molecule and non-polar. This picture which you have here, it shows the polar molecule of the water and non-polar molecule of the oxygen. As you can see here in this picture, this area of the water around the oxygen is partially negative and the area around the hydrogen is partially positive. But for the oxygen molecule, because the molecule is non-polar, it doesn't have positive and negative area here. The electrons are evenly distributed here. Let's go back to your book to talk about these type of the attractions which you have here on page 205. So what happens in this case? This is the oxygen molecule. In the oxygen molecule, the electrons are evenly distributed. When the oxygen molecule comes close to the water molecule, because this area of the water molecule is positive and this area is negative, it attracts the electron in the electron cloud of the oxygen. So suppose this is the electron cloud of the oxygen, this is the negative area, so it attracts the electrons toward itself. So what happened? The electrons in the oxygen comes here, and the other side of the oxygen depletes from the electrons, not completely but partially. So what happened to the oxygen molecule? This area of the oxygen molecule becomes partially negative because the electron has gone there, and this area of the oxygen molecule becomes partially positive because the electron has gone from here. So we have partially positive and partially negative area in the oxygen molecule. This is not normal for the oxygen molecule because the oxygen molecule is non-polar and it doesn't have positive and negative area. But what happened here? The water molecule induced dipole in the O2 molecule. So this induced dipole is temporary. It means if the water molecule goes away, again the oxygen molecule becomes in the normal situation, becomes non-polar. So now, what happens when the water molecule, when the oxygen molecule temporarily becomes polar? When it temporarily becomes polar, now this positive area of the water attracts to this negative area of the oxygen. So again, you have some type of the attraction between the water molecule and oxygen molecule. This type of the attraction is called dipole-induced dipole. So we can have dipole-induced dipole. The dipole refers to the water molecule because it has permanent dipole. An induced dipole refers to the dipole in the oxygen or nonpolar molecule because the dipole is induced there. It doesn't normally have the polarity. This type of the attraction is very important because by this type of the attraction, oxygen can be dissolved in water and the living organisms can use the oxygen in the water. Okay, let's go to the next type of the attractions which are available between the molecule. What happens if the molecule is non-polar and you don't have any polar molecule around? The same thing can happen for the noble gases. For example, the helium. The helium has 2 protons in the nucleus and 2 electrons which is moving in the 1s orbital. Okay, so the helium atom is also non-polar, exactly same as the non-polar molecules that we have, like carbon dioxide and CCl4. What type of the attraction do we have here? Okay, so in this situation, these electrons in the helium atom are moving around randomly. Most of the time, these electron cloud is, or the electrons are evenly distributed in the 1s orbital, but by chance at a fraction of time both electrons can be on one side of the helium atom. What happens in that case? This area of the helium atom becomes partially negative, the other area of the helium atom becomes partially positive because the electron has gone there. So what do we have here? We have momentary dipole. Okay, so it's momentary, it's not permanent. The electron again move to the other side, so again it becomes nonpolar and it would not have the dipole. But this happens by chance. When this happens on one of the helium atom, this positive area of the helium atom attracts the electron on adjacent helium atom toward itself. So what happened to this helium atom? This one is also becomes polar by induction. So if the momentary dipole forms here, it induces the dipole on adjacent helium atom. So now you have two helium atoms close to each other. This area is negative, this area becomes positive. For the adjacent atom, this area becomes negative, this area becomes positive. And you have attraction between this positive and negative area. So this is weak force happens between non-polar molecule, and it's known as London dispersion forces. This is the London dispersion forces because it happens because of uneven dispersion of the electron in the molecule. This is the weakest type of the attractions which are available between the molecules and noble gases like the helium. Why it is the weakest? Because the dipole which forms here is momentary, and after the while again this electron comes back to the other side, so you will not have the dipole, you will not have any attraction between them. So this type of the attraction, it happens, it forms, disappears, forms and disappears. That's why the London dispersion force is very weak. The London dispersion force available between all of the atoms, between all of the molecules, no matter if the molecule is polar or not. But for the non-polar molecule, this is the only source of the attraction between them. And in your book, you can have the definition of the London dispersion force here. It says the intermolecular attraction resulting from the motion of the electrons and temporary dipole. So this happens because the electrons are moving and it's also temporary. It's called London dispersion force. This happens in the non-polar molecules and polar molecules, but for non-polar molecules, this is the only source of the attraction, like H2, O2, Cl2, Br2. They are very weak, so that's why the London dispersion force, the molecules which are non-polar, and they have only London dispersion force, most of them are the gas at room temperature. The London dispersion force increases by increasing the size of the atom. So by increasing the atomic mass, the London dispersion force increases. So if you want, for example, to compare the boiling point of Br2 and Cl2, Cl2 is smaller than Br2. Both of them are non-polar. So the only force of the attraction between them is London dispersion force. London dispersion force depends on the mass. The boramine is more massive than chlorine, so it has stronger London dispersion force between its molecules, so it has higher boiling point. And let's talk about the last type of the attractions which we have between the molecules, and that is the hydrogen bonding. This is the special case, the hydrogen bonding. The definition of hydrogen bonding is given here. It says occurs when a hydrogen atom bonded to a highly electronegative atom. What is highly electronegative atom? The highly electronegative atoms are the phone elements: fluorine, oxygen, nitrogen. So it occurs when a hydrogen atom bonded to a highly electronegative atom is attracted to an unshared pair of electrons on the highly electronegative atom of another molecule. So what does this mean? Let me explain this for you. So look at here. In the water molecule, hydrogen is connected to the oxygen. So there is hydrogen bond between the water molecules. But what happens in the hydrogen bonding? In the hydrogen bonding, the hydrogen which is connected to an electronegative atom like the oxygen is attracted to lone pair of electronegative atom in adjacent or neighboring molecule. So the hydrogen bond is between one molecule and the other one. Hydrogen of one molecule is attracted to the lone pair of another molecule. But which hydrogen? The hydrogen which is connected to electronegative atom is attracted to which lone pair? The lone pair of electronegative atom of adjacent molecule. This is the hydrogen bonding. So the hydrogen bonding only available when you have NH, OH, and FH bond in the molecule. So you can have hydrogen bonding, for example, in NH3. In NH3, the hydrogen is connected to the electronegative atom of the nitrogen. So it attracts to the lone pair of the nitrogen, the lone pair of the electronegative atom on adjacent molecule. So you will have hydrogen bond here. So this type of the bond is strongest between all type of the attractions which we have between the molecules. So let's summarize that one. Between the molecules we can have dipole-dipole attraction, which is available between the polar molecules, and we can have dipole-induced dipole when the non-polar molecule dissolve in the polar molecule, like the oxygen in the water. And we can have London dispersion force, which is available between all type of the molecule, regardless if it's polar or non-polar. But for the non-polar, it's the only source of attraction. And we have hydrogen bonding, which is the strongest one. And the hydrogen bonding only forms in the molecules which the hydrogen is connected to one of these atoms. Okay, one more thing I have to add here. What type of the attractions are available between the ammonia? The ammonia is polar molecule. So in the ammonia you have dipole-dipole attraction. In the ammonia you also have London dispersion forces, because this is for all of the molecules. And also you have hydrogen bonding. So it's possible that for one molecule you have two or more of them. Okay? But for CH4 is non-polar molecule. Okay, so it's non-polar. It doesn't have the dipole. So for non-polar molecules, you don't have dipole-dipole attraction. You don't have dipole-induced dipole attraction because we don't have any polar molecule. The force of the London dispersion force, yes, you have it for that one. Do we have hydrogen bonding? Although it contains the hydrogen, but the hydrogen is not connected to fluorine, oxygen, nitrogen. It's connected to the carbon. So in this molecule, you don't have hydrogen bonding as well. So for the methane, you only have London dispersion forces. Okay, so this is all about the attraction forces which are available between the molecules, and we have finished this chapter. So we will go and we answer the questions which remains in this chapter, and then you will have exam from this chapter.